Okay, so we can get started. The class has shrunk because of the lab. I think the lab shouldn't be due on a class day. That's all I can say. But let's get started. Is the camera on? Okay, all right. So we are going to talk about web caching, except that the bottom seems to be cut off. Okay, fine. So I mentioned this very briefly last time. We are going to today talk about edge computing in general, but we are going to start with a very specific view of edge computing, which is using the edge to cache web content and deliver content from the edge of the network. So that brings us to this topic of web caching. Okay, so we know the standard client server model, that the client is a web browser that is accessing web content from a web server. Okay? Then we put a new intermediary in between, which is a proxy server that acts on the behalf of the actual web server. Okay? In this case, the proxy is going to send requests to the the browser is going to send requests to the web proxy cache. If the cache already has the requested content, you have a cache hit, and then the responses are sent back. If it's a cache miss, the proxy has to fetch the content from the web server, then it will get a response, and then it will respond back to the browser. That's the general model you want to keep in mind. Okay, so here is a picture of web proxy caching. Okay, so we see that there are not one, but many of these proxies. Each are deployed at the edge of the network or inside the local area network of various organizations. So you can deliver this content from very close to where the clients are. You'll see that the clients connect to their local web proxy. If the proxy has the content, it's going to send it back. This shows a special case where if it's a cache miss, the proxy can ask other nearby proxies first, which is what it is done here. That proxy is asking a nearby proxy to see if it has that content cache. If not, you're going to actually go get it from the server. Okay? This is called cooperative caching, where a set of proxies are going to collaborate with one another or cooperate with one another. In other words, the cache of each of this proxy looks like the union of all the content of nearby proxies, because you can either get it locally or you can get it from a nearby proxy. So this cache looks like a much bigger cache because it's the union of all the caches before you go get content from the server. We'll come back to cooperative caching in a few slides, but let's first talk about how we are going to maintain the consistency of this content. Okay? As I had mentioned last time, or maybe 2 lectures ago, whenever you replicate content or whenever you cache content, okay, if any of the clients in the system are going to update the content, then you are going to have to deal with this issue of making the content consistent. Okay. Okay. So in the case of the web pages that are cached at proxies are going to change over time. The content creator might update the web page. Maybe it's a news website. Whenever news stories break, they're going to go update the website. Right. So, whenever this happens, then all the content that is cached, or all the caches rather that cache this particular page, are going to be stale because they now have an older version of the web page. Okay? And our goal is to avoid serving stale content from the cache to the end user. Okay? Now I will mention this. There are 2 types of web pages that you are going to see in realistic web application. One is called static web page, another is called dynamic web page. Okay? A static web page is simply an HTML file that you have pre-constructed and stored on your disk. Okay? It's not actually changing unless the user goes and updates that page. Okay? Or a user program goes update. A dynamic web page is a page that is generated on the fly by a program. Okay? All of the pages that if you write a web application, okay, if you have a front-end web server, an app server, it is actually generating the web page on the fly. It's not. So if you ask for do a search on a specific product on an e-commerce site, there is not a specific web page that was already created and stored on the disk. Okay? The application is going to query a database, get back results, construct a web page on the fly, and return that page. Okay? Such pages are called dynamic pages. Okay? On the other hand, if you have a home page, okay, of your own, you might have created some content and stored an HTML file on disk. That page is not generated on the fly. It's been pre-created and stored on as a file on disk. Okay? So two types of content, static and dynamic. Okay? Web pages that are static can typically be cached at proxies. Dynamic web pages are not cached typically. Okay? This is because a dynamic web page, every time it's recreated, might have slightly different content. Okay? For example, if you go to an e-commerce site and you're logged in, it may enter your name at the top, showing that you logged in. If some other user goes to that same home page, they'll not get that exact page. They might get a slightly different page. They might have different recommendations, okay, which may be differ from user to user. So dynamic pages are assumed to change every time they're recreated. So even if the same user goes and accesses that page, they may get a different version of the page. So you do not cache such content. Static web pages, on the other hand, can always be cached. Okay? Even dynamic web pages, although the HTML of the dynamic web page is not cached, there may be objects embedded in it which are cached, like images, okay, or video objects. Okay? Those tend to be large, okay, and it's easier for a server to offload them to caches. So even though your HTML page may not be cached, large objects that are embedded in the page can still be cached, because those are often static. Okay? Images of products are not generated on the fly. They may have been pre-created and stored in a product catalog and so on. Okay? So we might have all kinds of content stored in the proxy. Question is, what happens when this content changes? How are we going to address the consistency of this object? Okay? And the object update frequencies may be very different. Some pages may be updated every few minutes, others may be updated every few weeks, and some maybe not with that often at all. Okay? So we have different techniques we are going to look at. Okay? Some of this you've encountered in your lab already because you are implementing cache consistency of some sort, but you will see some more concepts in today's lecture. Okay? The first dimension is when a web page is actually updated, how do you need to notify the proxy saying the web page has changed. Okay? There are two ways to do this. You can send what is called an invalidate message that just tells the proxy saying object has changed, throw it out from your cache. Okay? So it's just discarded from the cache. That's called an invalidate. Okay? Or you can send an update message which says the object has changed and here is the new version of the object. Okay? So now the proxy can discard the old version, but the new version has already been sent, so it can actually store it in the cache. And if new requests come in, then you can essentially just serve that content that's already cached. Okay? So we'll see when you want to send updates, when you want to send invalidate. That's one dimension. The other is who is responsible for cache consistency. Is it the job of the server, the web server, in which case we'll have an approach called push, or is it the job of the proxy, in which case you have an approach called pull. Okay? So it's either server push or proxy pull or client pull. Okay? So we'll start with the push-based approach. Okay? So in this case, okay, the server is going to track all proxies that have requested content from. Okay? Whenever a proxy makes an HTTP request to the server keeps track of the IP address of the proxy and the web page that was requested. So it has now a list of all the proxies that are caching any of its web pages. Okay? So if a web page is modified by a user, okay, then the server is going to just look for all the proxies that actually cache that web page, not other pages, but that web page. And then you can either send an invalidate or an update. Okay? So if you send an invalidate, you simply send a message saying web page is changed, discard it from the cache, or you can send the new version of the web page, which is sent to each of the proxy, and that's an update message. Okay? Now you might ask, when would you send invalidate, when would you send update? So if that depends on how popular that content is. Okay? If it's a less popular page, you may be fine sending an invalidate, because sending that update might be more work, might take more bandwidth, but then no one may actually access that page at the proxy. So you wasted some network resources sending a new version of the page when in fact it was not needed. In such cases, invalidate messages might be more cost effective. Okay? On the other hand, if it's a popular web page, then you may as well send a new version, because invalidating it simply means a request for that web pages are going to arrive at the proxy. It will cause a new cache hit, a cache miss, and then the proxy will fetch it from the server anyway. So you may as well just send the new version of the page, and then the proxy already has it, so you don't have to do extra work. Okay, so you can decide when to send an invalidate, when to send an update, depending on the popularity of that page, how much network bandwidth are you willing to spend for cache consistency. Is this clear? Okay. So what are some advantages and disadvantages of push-based approach? Okay. Push-based approach is going to give you tight consistency guarantees. Okay. It's not strong consistency, but it's fairly close to it, because as soon as the web page changes at the server can start sending either invalidate or update messages. So proxies will not have stale content. Okay. So you basically will ensure that proxies always serve fresh content. Okay. So tight consistency, because now a server knows exactly when the web page changes, and as soon as it does, it will send these messages to the proxy. Okay. So the other thing is, in this case, so the intelligence for consistency is at the server. Proxies are dumb. They don't actually participate in doing anything other than receive invalidates or updates and then just store content. Because all the work is being done by the server in terms of pushing either invalidates or update messages. Okay, so that's the advantage. Disadvantage of a push-based approach is that it has now made the server stateful. The server has to keep state. Okay, what is the state? The state is essentially a table that lists every proxy that has accessed web pages from it and what page was accessed. Okay, and that table, if you can think about it, can grow quite large, because you might have lots of proxies. They all access content. Every time you access a page, you add an entry to the table. Okay, and the table just keeps growing. Okay, now in this case, you don't need to. So first thing is, you have to realize that HTTP by itself is a stateless protocol. It does not require the server to keep state. If you implement server push at the server, you are going to now make the server stateful. Okay, and if the server crashes, that state is gone. Okay, so you have to ensure that whenever you keep state at the server, your state has to survive any failures, which means you might have to persist it at disk and so on. All of that is going to add overheads. Okay, that's the first problem. Okay, second problem is the state may need to be maintained indefinitely, where the server does not know when it can stop sending invalidates or updates to a proxy. Okay, when the proxy no longer gets any request for this content, or it uses cache replacement to replace that content, that's the point the server can stop. Okay, but there's no mechanism in server push for the server to know when that has happened at a proxy. Okay, so it might have to potentially keep sending invalidate and update messages for long periods of time, even though the proxy may not be interested at all in that content anymore. Okay, so state can be large. A state may have to be maintained for long periods of time. These are downsides of server push. The upside is you get tight consistency. That clear? Okay. All right. So the other approach, yes, your question. Okay, question is, while the invalidate message is in transit, the cache is already stale. Can you deal with this? Okay, so using server push, you can't actually deal with it, because even if the server instantly sends messages when the file is updated, there is still speed of light propagation delay for that message to reach the proxy. For that period of time, the proxy is going to have stale content. Okay, this is why when we talked about strict consistency, I said in practice it's really hard to achieve. We'll see that there is a approach. You can actually deal with that from some perspective, but it's not necessarily a good approach. But I'll come to that in just a moment. Okay, so let's talk about pull-based approaches. So here, the consistency maintenance is done by the proxy. The server is now not keeping any state or anything like that. It's the proxy's job to ensure that all of the cached content is consistent with what is at the server. How does it do that? Every so often or periodically, the proxy is going to poll the server. saying, I have this web page, has it changed? Okay. The server can reply with a yes or a no. Okay. Yes will basically means that you now have to invalidate your cache. No means that the cached content is still correct. Okay. And as it turns out, this polling can actually be done by a simple HTTP GET message. Okay. In fact, you use what is called a conditional GET. Okay. A standard GET just specifies a URL and you get that content. There's something called a conditional GET where you say get your URL and you keep a condition. There are many conditions. One is called if modified since, and you specify a date and a time. Okay. It says get me this URL if it was modified since this date and time. Okay. So it's conditional. If it has not been modified since that date or time, you will basically get not changed. But if it has been, you will get a version of that, a new version of that web page. Okay. So all that the proxy has to do is figure out when it fetched the content into its cache. Okay. And it can keep polling with the if modified since message with that date or time, so it knows whether the content has changed or not. And that's all it needs to do. Okay. Yes, question. Yes, good question. I'm going to come to that. The question is, why not just poll just when you get the request? Okay. So you could do that. In fact, if you did that, that's the only way you actually get strong consistency. Because the request comes, it's a cache hit. So you have the cache content, but you don't know if it's consistent or not. So you could do an if modified since request, check, is it still consistent? If so, you return the object that's already in your cache. Okay. And that will guarantee that you will never give stale content, because before returning any content, you always check if it's consistent or not. Okay. Very simple way of achieving strict consistency. So the question is, why would you not do that? That's a good question. So what is the downside of this approach? Okay. Could increase in latency. So the whole reason we are caching content at the proxy is the proxies are close to the clients, so they can deliver content faster to the client. Now, if before delivering that content, you have to go all the way to the server to check, you introduce another round trip time delay to go to the server, which is what you're trying to avoid to begin with. Okay? Then you may as well go to the server and fetch the content. Right? So good point in that you will, if you use that, you get better consistency, but you are going to increase latency, which is why you would not do that. Okay? Instead, you are going to asynchronously and periodically poll the server to figure out the content has changed. Okay? So that brings the question of, okay, how do you decide when to poll? How frequently are you going to do that? Every minute, every hour, every 6 hours? Okay? There's no good answer to this question. First thing is the server could potentially give you a hint. Okay? When the server sends you an HTTP response, it can embed something called a time to live value, or a TTL. Okay? A TTL is an estimate from the server saying the web page is likely to expire by this time because it's likely to change. Okay? So you could use the TTL as a hint to say when the TTL expires, from the server's perspective, the web page must have expired, so I better check. Okay? So that's one approach. Okay? But remember that that's not a guarantee. The server can't control when the web page actually changes. That's up to a user. The user can go change their web page whenever they want. Okay? So at best, this is a heuristic that can tell the proxy how frequently to poll. There's no guarantee that the page has actually not changed before the expiration. It may well change before the server thinks the TTL has expired. Okay? So it's only a heuristic, but you could use that heuristic to decide. But there are other approaches as well that we'll look at. Okay? But what you should be keeping in mind is that this is going to be weaker consistency than the server push, because between two polls, the content might change at the server, in which case you will have stale content. Okay? So the question is, how do you decide a good polling interval that minimizes the chances that you are going to have stale content? Okay? There are many ways to do this. Okay? One simple way is, let's find this polling frequency dynamically. Okay? Why do you need to find it dynamically? Because there's no good polling frequency for all pages. Some pages might change every 5 minutes. Okay, so that might be a news website. Others might change every few days. Our course website changes every few days when I post some new lecture slide. Otherwise, it doesn't change. So there's no point polling such websites every 5 minutes. That's a lot of wasted resources saying, Has the web page changed? Has the web page changed? Answer is almost always no. Only once every few days do you get a yes. Okay. But on the other hand, if you go to a news website, every few minutes you might have some breaking news updates or something like that, and the page is changing frequently. Okay. So you got to decide the polling frequency based on the update frequency of the page. If the page is updated more frequently, you got to poll more frequently so you can catch these updates and invalidate stale content. Okay. And if it's updated less frequently, you do it less. So yes, question.
Very small.
Okay, so let's see how to do that. Okay, so first thing is start with a conservative refresh interval, and the question is it very small or very large? You start with a small value. Okay, initially you know nothing about a page that you just fetched. You just fetched it, put it in the cache. You got to now start polling for it. You don't know how frequently you should poll. So let's say you set the poll frequency to be 1 minute, some small value. Okay, so you have 1 minute later you poll. Okay, at that point, and you send an IMS request, the server is going to either say yes or no. If it says yes, that means the page changed almost as soon as you got it. So you get the new page, or you invalidate it, and then you keep. If you got the new page, you again poll. Okay, but suppose the page did not change. The server says no. Okay, so then you say maybe next time I'm not going to poll after 1 minute. I'm going to poll after 2 minutes. Okay, so I increase the poll length. So I poll for after 2 minutes, and maybe you will again get a yes or a no. If you get a no, you increase it further. Okay, saying maybe I'll now do 5 minutes, maybe, and then 10 minutes, and keep increasing it until you find the time when the page actually changed. So you are probing. You fetch the page at a certain time. You try to find the next time it changed. That gives you some estimate of the time it's taking for the page to change. Okay? And then if you do that, then you basically fetch the page, and then you might reduce the frequency a little bit and keep probing. Okay? Yes, you have a question.
So this handles.
Okay, that's a good question. The question is, what I'm talking about polling here is to keep the content in the cache consistent with respect to the server. But how does the proxy know whether to keep the cached content at all? Maybe nobody's interested in it, right? So to understand when the proxy should maintain cached content and when not to, it has to track some statistics. Okay? For every cached web page, it has to keep track of how many requests have been seen over some interval of time, which is the request rate for that web page. Okay? If the request rate is very low, which means you're not seeing any requests, you might say this page is no longer popular. I'm going to evict it. Okay? So you can use popularity-based eviction. There are many cache eviction policies. You can just say, I don't need this page, I evict it. But on the other hand, if you see lots of requests for this web page, then you say it's highly popular, I better keep it consistent, and because I'm serving lots of requests with that web page. So in addition to figuring out how frequently to poll the server, the proxy has to figure out how frequently clients are asking for this web page, which tell it some notion of popularity, so it knows whether to even cache it at all. There's not a popular page, then why bother? Right? Nobody's asking for this web page, so you can discard it. But we'll get to that in just a second. Let me finish this intelligent polling approach. Start with a conservative value. Okay? Poll. If the server says not change, increase it. Keep doing this, and that interval keeps growing. At some period of time, you will find that the web page has actually changed. So then you might decrease it slightly and then poll at that frequency, and then essentially figure out if that is the right one or not. Okay? And keep in mind that the reason this approach is adaptive is the right frequency is not fixed. It's not like every 5.5 hours a web page is going to change. That itself might depend on how that content is changing, how the user is updating their web page or some content. So the update frequency might itself fluctuate over time. And this approach will figure it out, because if it finds that the web page has changed, then you basically reduce the polling frequency. And if it changed again, you reduce it further. So you essentially, your polling frequency is going to follow the update frequency of the web page. Okay? In some loose fashion. You can't actually ever find it accurately, but you can find it in some loose manner and try to make sure that the network resources for cache consistency are optimized. So you don't send either too frequent messages or very infrequent messages. And it's basically going to adapt based on what the page actually is seeing in terms of update rates. Okay. Any questions on this? Okay. So that's our adaptive poll-based approach. So let's talk about advantages and disadvantages. Okay. Simple to implement. As I said, you can use standard HTTP messages between the proxy and the server, because you can use conditional get messages, which are also called if modified since or IMS messages. Okay. These are IMS gets. Okay. So you can just use that to poll. Okay. There's no additional technique needed to do this. Server remains stateless. Okay. There's no state at the server. The job of the proxy to keep polling the server. Okay. This is resilient to server failures. It's fine if the proxy fails and wakes up, it just starts polling again. Not a problem. Okay. The disadvantage is you are going to get much weaker consistency guarantees than the server push approach. Okay. Because time to live value, adaptive polling, all these are heuristics. The web page might change at any time. It won't be discovered until the next poll. Until that period of time, you're stale content in the cache and you're serving stale content to your users. Okay. So that's something you have to keep in mind. Okay. And as I said, you can get strong consistency only if you poll before every HTTP request, which was the question that was just asked earlier. If you go and poll the server every time a new request comes in, yeah, you get stronger consistency. But that adds latency and it defeats the purpose of proxy caching to begin with. Okay. So this requires more sophisticated proxies so you can poll appropriately. The message overhead may be higher. Okay. Remember, in server push, you have the optimal message overhead. For every update on the server, there's one message going to the proxy, either a notification or an invalidate. Okay. In the proxy poll approach or pull approach, you may get arbitrary number of poll messages before you discover that a web page has changed. So the number of messages that get exchanged is going to be always higher than the server push. Okay. If you find the right poll frequency, it can be reduced, but you can never get it any better than the server push approach. That clear? Okay. So now let's look at a hybrid approach. Okay. Server push we like because it has stronger consistency guarantees, but you said it was stateful. You have to keep state for long periods of time. All that's a problem. Okay. Proxy push was much simpler. It was job of the proxy, but you had weaker consistency guarantee. Okay. So we can put these two things together and we get an approach that is a hybrid. It's called leases. Okay. So let me explain what a concept of a lease is. It's a more general concept in distributed and operating systems. Really has nothing directly related to web caching, although this is the first time we've encountered it in this class. Okay. So what is a lease? Okay. A lease is similar to this physical construct. Okay. Just as you sign a lease for an apartment to rent it, a lease is essentially a contract between two parties, okay, for a period of time. Okay. Every lease has a duration. So think of a timed contract. So it's a contract that's valid for some period of time, and it's an agreement between two parties. Okay. In our case, okay, in this case, a lease is an agreement between the server and the proxy, and the server says, I will send you invalidate messages for this period of time. Once the lease expires, server will stop sending invalidate messages because there is no more a lease. Okay. So that's the contract. In this case, the contract is one where the server agrees to send notifications as soon as the object changes. But you can have leases for all other kinds of things in distributed systems and operating systems. If you want two components to essentially have some agreements for some period of time, you can implement this through this concept of a lease. Okay? And when the lease expires, it's the job of one of those two parties to say, should it just expire or should you renew the lease? It's the concept of renewing the lease, which means that you can ask for a new contract for another period of time. Okay? The same would be true here, where when the first time, okay, let's say the client sends a HTTP request to the proxy, it's a cache miss at the proxy. So the proxy's got to go get it from the server. Okay, so you'll see that it sent a GET request and plus it asked for a lease. Give me this web page, give me a lease on this object. Okay? The server is going to send a standard reply, is going to give you a lease and say, here's a lease, 5 hours, okay, whatever the period is. Okay? And then for that period of time, whenever the object changes, okay, you are going to send invalidates or update message. Okay? So in some sense, it's like a server push approach, but you don't keep state indefinitely. The state expires when the lease expires. Okay, so you don't need to have very long tables where some proxy asked for this page 6 months ago and you're still sending it messages. Okay, you don't need to do that. Once the lease expires, it's the job of the proxy to say the lease has expired. Should I renew the lease? Okay, now the proxy can figure out, is the content still popular, because it's tracking its frequency of gets from the clients. The object continues to be popular, it can just renew the lease, and then the server will send it a new lease and then essentially send it more invalidates. But on the other hand, the popular object is no longer popular. Maybe it was at one point, but now it's become cold and not popular anymore. And you can just let the lease expire and you won't get any more messages from the server. You can discard it from your cache. Okay? So all of this essentially can be done using the leases approach. Okay? So lease is always provided on the first request only to proxy, not to browsers. Send notification until expiry. You need to renew the lease if you want to continue to get messages. Okay? Now the interesting thing here is that the reason this is a hybrid approach. First of all, both the proxy and the server have to participate. The job of the proxy is to figure out if you should renew the lease and ask for the lease the first time. The job of the server to keep sending messages until the lease expires. Okay? But the interesting thing is the lease duration allows us to control how this approach actually behaves. Okay? Let's say the lease duration is set to infinity. Okay? Very long leases. Okay? This approach degenerates to server push. No difference. Server push is essentially a leases approach with all leases being infinite duration, because you just keep the entry in your table forever and you have to keep sending messages. That was the problem with server push, right? But you can make leases longer and longer, and this will become more and more like server push. Okay? On the other hand, if you essentially set the lease duration to 0, that's almost like polling. Okay? You ask for a lease, you say here's a lease, it expires immediately, and then the server client, or rather the proxy, has to send another if modified since get request and ask for a new lease. That's like polling, right? So if you make the lease duration small, this approach begins to look like poly based or a proxy pull approach. If it's infinite, it's a server push approach. Okay? Which is why, depending on the lease duration, you can make it look like one or the other. Okay? And the efficiency of the approach depends on the lease duration. Okay? You can ask, how is the server deciding the lease duration? Just as we said, how does the proxy decide the poll duration? How long should the lease be? Right? So we can use various statistics again to decide this. Many different policies. Okay? You can say it's going to be dependent on the age of the object. Okay? So the object age is basically if what was the last time since it was modified. So that's the age. So it's been 5 days since it was modified, or 5 months since it was modified. That's the age of the object. So you can decide the age of the object to set the lease, say maybe if the object is updated less frequency, you might give either a shorter or a longer lease depending on your policy. Okay? You can decide it based on popularity, okay? Or renewal frequency, saying leases that are more popular are likely to be renewed more frequently, because rather than making the proxy renew it often, just give it longer leases so it reduces the work for it. Okay? So in some sense, renewal frequency is directly correlated to actual popularity. So more popular objects give longer leases so you can keep that content fresh, because the object is already popular. So keeping it fresh on in the proxy is to your advantage. Okay? So essentially that's the approach. You can decide it based on server load. The load on the server is high. You can say, I'm going to give shorter leases. Otherwise, every time there's a change, I have to send all these messages to lots and lots of proxies. That adds overhead. That increases the load on the server even more. Okay? So during periods of high load, you might decide to give shorter leases to reduce the overhead. Okay? During low load, maybe you can give longer leases. All kinds of policies exist. These are just 3 examples of lease-based approaches. So popularity, age, load, and think of other policies as well. Questions on leases-based approaches? Yes. Okay, what is the age-based lease? First of all, what does age mean, right? Age of a file or web content is essentially the time since it was modified previously. Okay? So if it was last modified 5 days ago, you look at the last modified time of the file, and the difference between that time and now is the age of that file. Okay, so older files means they have not been modified. Okay, younger files means they have been modified recently. That's all it means. Okay? So you can decide the age to essentially understand how frequently the object is being modified. So if there are shorter objects, okay, you might say this object is getting modified more frequently. So maybe I should send more frequent messages so I can give either a longer lease or something like that. Okay. On the other hand, if it's an old object, okay, you can give a long lease, but no messages is going to be sent to the proxy because they are not going to change, right? Because the idea here is the age is some indicator of the update frequency. Okay? Not an exact indicator, it's only telling you the last time it was changed, not telling you the rate at which it's changing, but it's some indicator, right? The object was changed 5 minutes ago, maybe it is newly updated. It might get updated again. At least it's fresh. If it was 5 days ago, it tells you something. So you can use the modification times of files to decide the age, the length of the lease. That's all it's saying. Okay. Anything else? Okay. So that is the leases-based approach. Now we'll, yes, question. Yeah. So the question is, if the file is modified more frequently, can the age will be lower, so you might have to give longer lease. So this one says give longer leases to longer lifetimes, but you can do the exact opposite. Okay, you might say if it's shorter, okay, depends on whether you want to reduce the load on the server or not. That's the criteria. Okay, you might say it's more frequently accessed, so if I want to do more work to keep the content fresh, I should give longer lease, but increases the load. Or you might say, I don't want to send too many requests. So if the object is getting modified too frequently, I might use something like some heuristic like this to say, I'll give less shorter leases to reduce the overhead on the server. Okay, this is giving you one example, which says the larger the expected lifetime, the longer the lease. But you can do the exact opposite, saying shorter the expected lifetime, longer the lease, because it's more frequently updated. Okay, that policy could be either two different age-based policy. Let's put it in. Yes, question.
Say a proxy server. Say, okay, I want to just.
Okay, the question is, if a proxy evicts an object from the lease, can the lease be cancelled? At the as designed here, there is no cancellation mechanism, but of course you can add one. There's nothing to prevent you from adding that to the protocol. But there is no reason that there is going to be any problems. Even if you evict the object, you'll just get some messages to invalidate it. You can ignore those messages. Okay? It is wasted overhead until the lease expires. Ideally, if you have an active lease, you should not evict the object. But if you do for any reason, sure, you can. There has to be either a way to cancel the lease, or you will get some wasted notifications from the server. One of those two things will happen. Good point, but I think as designed, the approach did not have a cancellation mechanism. Okay. All right. Now let's talk about not one proxy talking to the server, but several proxies talking to one another and talking to the server. That's called cooperative caching. Okay. So your caching infrastructure, okay, can have multiple proxies. You might say, let's set up a web proxy for computer science. Let's go put one in engineering. Okay, there will be some content cached there depending on what the faculty and students are browsing there. There may be some other content here. So if you have a cache miss at your local proxy, rather than going to the server to fetch it, if there's another nearby proxy, it may be faster to ask that proxy for the content. Okay? That may still be faster than going to a far-off server. So there are scenarios where cooperation between proxies, where this deliver local content to other nearby proxies, has advantages. Okay? So this concept has been generalized to the notion of content distribution networks, CDNs, which we'll talk about in a moment. But let's first talk about how you can get the proxies to cooperate with one another. Okay, so I'm going to show you an example. Okay. of a server. So this is a hierarchical proxy cache. There's a server at the top. Okay, this is essentially a tree of caches where there's a parent cache, there's the root cache, and 3 leaf caches or child caches. Okay, a system of 4 cache servers, 4 proxy servers. Okay, and these things at the bottom, they are essentially clients. Okay? And there are many open source systems that do this. One is called Squid, another Harvest. So you can set them up either as standalone caches or cooperating caches. This is an example of cooperating cache. So I'm going to show you how this is going to work. So here is essentially a client that's asking for web page A to this cache. If it is a hit, then you are going to get it immediately. Problem is solved, no cooperation needed. But let's assume it's a miss. Okay? So now if it's a miss, this cache is going to ask these other caches and its immediate parent saying, do you have this object? You see something called ICP on those arrows. ICP stands for Internet Cache Protocol. Those are not quite HTTP requests, but those are essentially like HTTP GET requests, but they're asking, do you have this object in the cache? Okay, and then if one of them has it, then you'll get it. If not, then you'll have to continue this recursively. Okay? So you will get back requests. Let's say the requests all say, no, we don't have this object. Okay? So now you essentially try to ask your local caches, you didn't get it. So what you're going to do is you are going to forward this request to the parent saying, I got this request for A, can you serve it? Okay? Now, if this was a multi-level hierarchy, this will repeat recursively. The parent might actually ask its siblings and its parent, okay, saying, is there an object here and so on. So this can be a multi-level hierarchy. This is just a one-level hierarchy. We know that the parent doesn't have it because you are already asked it with an ICP message. So what will the parent do? It will go ask the server, sending HTTP message. Okay, response came back to the, and then you send it back down, and then you essentially send it back to the client that asked for it. Okay, so this is a simple example of every time you ask, if you get a request, you don't have it, you can ask your siblings, you can ask your parent. If not, you forward it up and have them resolve it, and eventually you'll get the content. Is that clear? Okay. So what problems do you see with this approach? Yes. And lots of requests. Okay. If you get a hit somewhere in the hierarchy, all these requests give you a benefit. Okay, maybe you got it after 1 or 2 attempts. These are still nearby caches, so the request will be fine. But if all of them come back and say no, then you spent a lot of messages, and then you're going to get that request from the server, is going to flow down the tree, and meanwhile the user is waiting for their web page. Right? Web page is not loading. Okay? It will take a very long time because proxies are busy trying to figure out, do you have it? Do you have it? Go get it from the parent. Parent will get it from the server. So if you have what is called a global miss, which means nobody has it. Global cache miss, very slow. Okay? Here you exchange maybe 10 messages just to figure this out to get it from it. It would have been much faster to just go directly to the server and get it. The whole point of proxy caching was to load pages faster by keeping content close by. You actually made it slower. And there's a global miss at least. If you have a local hit or something like that, that's not a problem. Okay? So we can't actually use this scheme if you really want to deliver content very quickly to users. Okay? So what can we do? How can we do better? Yes. Okay. So you could reduce this duration by increasing the lease duration. So first of all, I should mention that this doesn't actually involve leases. This is simply a pull-based approach. There is no lease in here. Okay, consistency is not maintained right now, shown in this picture. This was simply saying, I don't have the content, I got to get it. Okay, that's a different question about if I have content cached, how is the server going to tell me when they're updated? Okay, that you might have to do through leases. It doesn't show it here. Okay, but that's orthogonal. That's cache consistency maintenance. This was simply trying to serve a GET request, and it got into all this extra work just to get a page. Okay, yes, but Okay, question is, why could we not use this if there are only popular web pages? The probability of getting a hit is higher. Absolutely true. All popular web pages are not going to see this problem because very likely they are there almost at every cache. So you ask for the page, it's a hit. Okay? But you can't assume that users are only going to ask for popular web pages. Right? You can browse for any web page of your liking. Your browser is going to ask the proxy. That's how your browser is configured. Browser thinks a proxy will give you a web page faster. So every request your browser makes goes to the proxy. Okay. And then if it's not popular, you have this problem. If it's popular, there is no problem. Yes. Okay. So you could essentially send every request to the proxy and the server, whichever replies faster, you get it. Great approach, except that you have not reduced any load on the server. Every proxy request also goes to the server. So even if it's a hit, you're going to waste resources. Keep that in mind. If it's a miss, that works very well. But you don't know whether something is a hit or a miss. Okay, there's something. You can limit the depth. You can say, I'm only going to ask my siblings. If there are misses, I'm going to go directly to the server. Don't recurse. It'll be faster. Okay, but we can make it even better. Yes. Okay, so that's the similar thing that what was sent. You only ask some nearby proxies. Okay, also possible. Okay, but let's see a slightly different approach that basically uses concepts that we've already seen. Okay, which is why ask at all? Okay, why not keep information of what is there in my nearby caches? Okay, so in other words, I am going to keep a table at every proxy that says what is cached in my cache and what is cached in my sibling's cache. Okay, so instead of sending an explicit ICP messages, I'm just going to do a local table lookup. Here's a web page. Do I have it? No. Does somebody else have it? But I'm still looking up a table. Okay, if the table says a hit, I'll just go get it. If the table says miss, I go get it from the server. Okay, so by just keeping a table, I've just avoided repeatedly asking proxies, do you have it? Not. I know precisely what is there in every proxy's cache that's near to me. Okay, is that clear? Okay, so this creates other complications, but here is what's going to happen. Okay, I ask for A, okay, and I look up the table there. You say that A is actually stored at node X. Okay, so I'm going to basically just go get it from X. Okay, and then I send it back. Done. Okay, except that you have to keep in mind that if A got invalidated here because of any cache consistency, that might be a stale entry. So my table itself might be stale because the proxy hasn't notified me that it discarded that content. So it might be the case that I have a table entry saying A is stored at X. Okay, X might say I don't have it anymore. I just discarded it. In which case I still have to go get it from. Okay, so a miss is at most 2 hops if I get it wrong. If that table entry is wrong, it's either 1 hop where either I say there's nobody has it, the table doesn't show it, I just go directly from the server. That's 1 hop. Or at worst case, I send it off to a nearby proxy. Proxy says, oh, I just discarded it, don't have it. Still 2 hops. Not as bad as the previous case. Okay, lookups are local. Okay, hits are at most 2 hops. Okay, misses are also at most 2 hops. Okay, so that's all good, except that now we have created another problem where not only is the cache supposed to be consistent, this table also has to be consistent. As objects are fetched and discarded, you have to at least send a broadcast to all your nearby nodes saying, look, I just got this new content into my cache, add it to your table. Or I just discarded this content from my cache, remove it from your table. Okay? So long as you do that and these tables, which are essentially hash tables or directories, are kept consistent, everything is good. Okay, but if the table is stale, you haven't gotten that message, updating it, you might go off looking for a content from some node that no longer has it, and it slightly slows down your misses. Not as bad as the previous approach, but still you can avoid that by ensuring that consistency of the table and consistency of our cache are both maintained. Okay, flat hierarchy, meaning flat caching architecture, no hierarchy. Okay? You see that there's no parent, it's just a set of caches that are just talking to one another. You can make arbitrary groups and do this. Okay? So here is our global miss. So I go, there's no entry for B. I ask for B, I go get it, and I'm done. That's my global miss. Okay? So nothing, you don't need to ask 20 caches before you figure out I need to go to the server. Any questions here? Okay. So that is a different caching architecture. Okay, either of these could be used depending on the scenario. Okay. So we are going to take that discussion of web proxy caching and expand that a bit. Okay. So all of this web proxy caching was a very popular topic of research in the early 2000s, about 20 years ago. Okay. The whole area has now evolved. It's now called edge computing. Okay. So what does edge computing mean? Edge computing essentially says that I can put computing resources or storage resources at the edge of the network. Edge of the network essentially means close to users. Okay, that's the network edge. So wherever the users connect to the network, either through your Wi-Fi or through your local LAN, that's the edge. And when the packets go into the network, that's called the core of the network. Okay? So in edge computing, you're going to put resources at the edge of the network and provide all kinds of services from the edge. Okay? And the idea is that if the services are latency sensitive, okay, the speed at which you deliver the service matters, then putting the resources at the edge is faster than going to the cloud. Okay? Because the distance to the cloud, the latency to the cloud is going to be higher than the latency to the edge. Okay? Because the edge might be 1 or 2 hops away, the cloud might be 10 hops away. Okay? So the edge is closer. So if you can deliver some service from the edge, it's going to be faster. Okay? That was the rationale for putting caches at the edge, because you can actually get your web content faster from 2 hops by going 2 hops than going 10 hops. Okay? But you can do other kinds of things as well. You can put entire applications at the edge. You don't need to just put a cache at the edge. Okay? So edge computing is a paradigm where applications run on servers at the edge of the network, okay, and deliver this service. Okay? So here significantly lower latency than remote cloud services. You might actually have higher bandwidth from you to the edge than you to a remote site on the internet, because then you are bound by how congested links on the internet path are. Okay? So you might get better bandwidth. You can tolerate network failures because you might still be connected locally to your edge, even though there may be outage somewhere in the network and so on. Okay? Many different benefits of edge computing. You have to remember that edge computing is now actually an extension of cloud computing. Okay? The cloud computing paradigm, although edge computing was initially designed for doing something like caching web services or helping mobile devices, as we will see, now the way this is actually done is cloud providers have themselves put servers on the edge. Okay? Just as you can go and create an instance on an EC2 instance or an Azure cloud, you can ask each of these cloud providers saying, give me a server close by. Okay? There may be all kinds of edge location. Amazon has an edge site in Boston. Okay? So you don't need to go to Washington or California. You can just say, give me an instance in Boston, and they'll give you a VM that exactly looks like a cloud VM, except that is nearby. Okay? So you can run your services close to where you are instead of further away. Okay? So cloud computing has now adopted edge computing, and you can deliver cloud-like services. Infrastructure as a service clouds are now deployed on the edge as well. Okay? And lots of applications are now using cloud-based edge servers instead of deploying their own edge servers to provide exactly low latency services to their end client. Okay? So that's something you want to keep in mind. We'll come back to this in a few minutes. Okay? But before we do that, let me explain a little bit of history of where all this came about. Okay? So the origins of edge computing have come from 2 different fields. Okay? One is mobile computing, and the other is web caching. Okay? The relation to web caching should already be clear. Okay? The old days, they started by putting these servers at the edge, and they were just caches that were caching content. Then they said, why stop there? Why can't I run my entire application that's running on the server? Let me run that whole application nearby. Okay? So it's no longer a cache, it's actively running some application like a multi-tier application or a microservice. So you can directly make requests, okay, and then the request gets serviced. Okay. So essentially, proxy caches evolved to providing more sophisticated application, running more sophisticated application on this edge server. That was one evolution part. Okay? And essentially, those web proxy caches also became content delivery networks where there were commercial companies that went and deployed thousands of caches and said, I'm going to give you very low latency. You just have to buy my service. I'll take all your content and put it on my edge cache and will be delivered at low latency to end users. Okay? Those commercial services also saw opportunity saying, why stop at caching? Let's allow customers to deploy applications on the edge. Okay? So that was one way edge computing came about. And then there was a separate evolution from the field of mobile computing. Okay? Here, in the old days, now you have smartphones that are fairly sophisticated, powerful, but 10, 15 years ago, phones did not have that much computing capability. Devices like laptops did not have significant computing capabilities, that limited battery life, and maybe the processors were not as powerful and so on. Okay? So then the question was, what if I want to run a high-end application on my local mobile device? Okay? I don't have the resources. I may not have energy. I may not have battery life to run it for long. I may not have CPU capacity to run it for long. So what do I do? Okay? So one approach was what was called computational offloading or compute offload, where he said, why run it here? If there's a nearby server that's at the edge that's powerful, let's run it there and it'll just send me results. Okay? So I offloaded my entire mobile application to my edge server. The edge server executes it. I'm simply sending requests or getting results from. Okay? So that became a popular approach for augmenting the capabilities of low-end mobile devices. Okay? The mobile devices are no longer constrained by what was on them. You could augment their capacity by saying, I have more compute nearby, more storage nearby. You want to store a lot of data, you don't have disk space here. Here's another server that can give you a lot more storage. And it's fairly close, so you can get all that data and access it at low latency. Okay? So low latency offload became important. Okay? So that's even true today. Okay? Even though your phones are more powerful, your devices are more powerful, all kinds of new devices are coming about that still require this capability. Okay? Mobile AR and VR is a good example. Okay? You can see now there are all kinds of mobile AR, VR headsets that you can wear. Okay? They have fairly high compute needs. Okay? They need to render high resolution content at very low latencies. Okay? That will require a high-end graphics capability. That's going to essentially require compute capabilities. That device is not going to have capabilities of a laptop or a high-end machine, but you could have an edge server that has GPU that's rendering all that and just sending you the bits. Right? That's going to give you, now it has to be very close because the latency is very sensitive. If the user even turns their head, you need to make sure that the scene that they're viewing is appropriately modified. So very low latency needs, but this VR headset does not actually have the compute capabilities you might need. So offload is still a good example use case, okay, for these types of applications. So although the need for using edge computing for things like phones may have reduced somewhat, there are all kinds of other new devices that are coming about, IoT devices of all kinds and AR, VR devices that still have that need. Okay? So mobile computing still relies a lot on edge computing, okay, for that reason. Okay? So both of these led to the evolution of edge computing. And then, as I said, cloud computing essentially took over and they deployed lots and lots of servers. So you can now get these services just as you can get any cloud server, not services, rather servers, and then deploy services on them. Okay? So we'll look at content delivery networks, and then I'm going to come back to edge computing and then show you where we are today in the world of edge computing. But let's talk about CDNs, which are essentially an evolution of web proxy caching. Okay? So what is a content delivery network? Okay, essentially, it's a global network of edge proxies that some commercial company has deployed in many, many networks all across the globe. Okay? And these proxy caches serve a lot of content. Okay? They no longer serve HTML content because that's really low end, low bandwidth content. They are designed for high bandwidth content like videos, audio files, high-end graphic images, and so on, which if you deliver from the edge, actually speeds up the load time on browsers or increases quality of experience and so on. Okay? So streaming high definition content from a far off server, you may have congestion on the network, so packets may get dropped, all kinds of problems might arise. But if you deliver it from the edge, perhaps there are only 2 hops to go. The probability of something going wrong is lower. Okay? So a lot of these content delivery networks are designed to serve these high-end content, okay, images, video, audio, and so on. Okay? If you take the Akamai CDN, which Akamai is a company that provides a commercial content delivery network, they have more than 100,000 servers deployed in more than 1,000 networks in 80 different countries. Okay? So practically every organization will have some caches that they're deployed. They've been doing this for many, many years. So they have one cache deployed at UMass, for example. Okay, you might be going to some website, but a lot of the content might be coming from your local cache. Okay? And they might have one in your cellular network and one in your cable network and so on. Okay? So content providers, which are websites, are essentially customers of CDN. These are all news sites that have images. Okay? They could be graphic-rich online stores, all kinds of streaming services essentially use CDNs to deliver content. You don't have one server that's doing it. You have lots and lots of edge servers that are essentially doing it. So you are deciding what content to offload to the CDN, what applications can be sent to CDNs and so on. Okay? Now, the way you might say, okay, how is consistency handled in this case? Okay? So as it turns out, most of these services are essentially delivering video and images and so on, not HTML content that is changing frequently. So it's already a different problem. Okay? And the way you deal with consistency is you essentially, if the image, if the web page, that's of a news site, wants to have a different front image on their banner headline, okay? All that they're going to do is they're going to update the web page and they're going to have an embedded different image. Okay? When the browser loads it, okay, now it basically has to get a different image from earlier, and then you just go get that new image from the CDN. The old image is still there, but because it's no longer embedded in the page, the browser is not going to fetch it. And the page is coming from the server, not from the CDN. Okay? So you basically go get the initial HTML page from the server. There are all kinds of embedded images in them. Those embedded images are stored in the CDN, and then you just go fetch them. And if I change it in the server, I still now just have a different link. I load a new image. So I don't have the problem of actually making sure that whenever something changes, I have to push it, because things like images, videos, they don't change. You might just throw it out and put a new one in your HTML file, but you are not going to necessarily go update it. Okay? And even if you update it, you can just give it a new file name, so it becomes a different image from the perspective of the CDN. Okay? So consistency is responsibility of the content provider, but it's not the same problem as what we saw earlier, because these are used to send other types of content, not HTML pages or things like that that are changing frequently. Okay? So somewhat different way of dealing with delivering content and ensuring consistency. Okay? So users are going to access the website normally. Okay? Unlike web proxy caching, where your browser directly contacts the proxy cache because you configured it in your browser. You went into the settings and say, here is a proxy. So then all your web requests are going to the proxy, not to the server. In this case, in the CDN case, you still go to the server to get the initial web page. And the server has embedded links that are pointing to the CDN. So you might have a link in a web page that says cdn.com foo.mpeg. Okay? So then when the browser tries to load that content, because that URL is pointing to a CDN, which is where the content provider loaded their video, it'll come directly from that. So you don't need to worry about actually having browsers talk directly to proxies. So it's basically done through embedding links that point to the CDN rather than the server. Okay. Is that clear? Okay. All right. So let's talk about how will now, because of this, this is now causing browsers to implicitly go to proxies because you're not explicitly configured a proxy in your browser. Okay? So how does the browser know if I have 100,000 caches in the CDN, which one to go to, okay, to get my content? Because it's replicated at lots and lots of proxies. So you have to figure out how am I going to go get to the nearest one. Okay, because that's not going to be told to you by the server. You have to figure this out. Okay. So the way you are going to do this is you are going to essentially use a load balancing technique that is embedded in the domain name lookup. Okay. Here's how it's going to work. Okay. Now let's say the browser wants to go and load this video. Okay. So it's essentially saying cnn.com/newsvideo.mp4, except that you are going to now resolve this to a CDN proxy cache rather than the CNN's main server. How is that going to work? So your browser is going to make a DNS lookup to find the IP address of that server. Right? Now, we will assume that this is not a normal DNS server. It's a special DNS server that essentially, whenever it gets a request, it tries to figure out where the request came from. Okay? Because a DNS request come with IP address. Okay? My browser is going to make a request to a DNS saying, this is my IP address, I'm going to look up CNN.com. Okay? That DNS server will look up my IP address and say, this is a machine in the UMass network. Okay? It's located in Amherst. Okay? So it basically geolocates you, tries to figure out where you are, and then say, what caches do I have nearby? Okay? And you'll find a cache somewhere that's close by. And then it will give you the IP address of that cache instead of the real server. Okay? So by just doing a DNS lookup, okay, different clients are essentially sent to different caches because the DNS server just sends back different IP addresses for the same machine name. Okay? Normally, if you just go and do a lookup on umass.edu or www.umass.edu, you'll get one IP address. That's the IP address of the server. Okay? In the CDN case, okay, you have a special DNS that is automatically resolving the IP address to a nearby cache location automatically for you. Okay? So now your browser, without doing anything, it just does this normal DNS lookup. It got sent to a nearby proxy cache. It connects there. It asks for this URL, does a GET request, gets it, and is done. So it's transparent to users. It's actually transparent to the browser. All of the intelligence is now actually embedded in the IP address lookup, the DNS lookup. Okay? So the way you are going to do this is the CDN is going to have a two-level load balancing policy. There's a global load balancer that's done at a DNS level. That's saying, okay, here is a DNS request from where is this client? I'm going to send them to this edge location. Okay? So you'll go to an edge location that's nearby. Okay? So now that edge location might not be a single proxy cache because it's a large service. It may be a small cluster, maybe 10 machines or 5 machines, some small cluster that has a bunch of content cached. Because if you have lots and lots of videos, you can't put them on one cache. You might have to have a small cluster of caches. So when the request arrives at that cluster, you do a local load balancing, says that looks like a web cluster. So here's a request, which of my servers should serve it? And then you map it to one of the servers. Okay? So two-level load balancing. Okay? First level is DNS. Okay? You are going to ask, where should this client be served from? I have all these proxies all over the world, which is the nearest one, and you send it there. And then once the request goes there from the browser, okay, the local load balancer is going to say, there are 7 of these caches, which one should serve it, and then you map it. Okay? And then you get the content from that. So all of this is going to happen without you having configured a proxy or anything like that. In fact, this is how a lot of your content is actually being fetched. Okay? You might not know, you might think you've gone to CNN or New York Times or whatever your favorite website is. And maybe the main page came from that server, but a lot of the images and videos, they are coming from proxies based on something like this. Yeah, often, not always, but often. Okay? So different users will get sent to different locations, so that automatically balances load across proxies. Users go to nearby proxy, so they get better performance. The load on the server is reduced because you could always go to the server to get the content, but now server has offloaded all of that work to a lot of proxies, so you get much better scalability of your application. Yes, question.
The local load balance using
Yeah, the question is, if it's a local load balancer, does it use the concept we looked at, which is least loaded, round robin? That is exactly what the local load balancer it does. It's a cluster. Okay, so long as content is replicated, okay, you can send it to any of the caches. If it's not, you have to look at the URL and only send it to the subset that have it. But so long as replicated, you do round robin or least load. Yes. Anything else here? Okay. So that is CDN request routing. So you can essentially say which proxy answers a client request. Ideally, closest proxy use DNS-based approaches. You can essentially have all kinds of techniques to propagate notifications. If you want to invalidate content, you can use multicast and whatnot. As I said, if you're only using things like images, they're not going to change, but you might have to delete them from the cache if you don't need them, because you are going to be charged based on how much content is cached. That's a commercial service, so you don't want to keep old items hanging around and I'll pay for them. So you might want to send invalidate and say, I don't need this cache. This web page is gone from my system, so just throw out this content. Okay, so you can send notifications. Okay, still an active area of research. There are many papers being written on how to do this in a scalable way and so on. And there are commercial services as well. Okay, so that's CDNs. Here is a picture that showed you what I was talking about. This middle thing is your client, okay, and then you're going to go to the server that's here. Okay, get the HTML page. Okay, so you get your HTML page, okay, and then you're going to essentially go to your local DNS server saying, I need to load this image in this page. That DNS server is going to send you the CDN server. CDN server is going to say the IP address of what is the IP address of the client. You said the client is at this location. Based on IP address, you try to find the location and then find essentially a CDN server, which is your proxy, and say that's the nearest one. Go there and get the content. Okay, so that's exactly what I said before, shown in the picture. Okay, and if the CDN server does not have that content, it's a miss. Of course, it can go and fetch it from the origin server and then load it exactly like any other proxy. Right? Okay. So I talked about this already, so I'm going to skip this, talk about mobile edge computing, and then we mentioned some of this, but I'll talk about this again so that you understand how edge computing is being used in today's world. So as you have more and more of these latency sensitive applications, edge computing has essentially become a popular way to deliver these applications. Okay, so I talked about augmented reality, AR, VR, and so on, specifically from mobile devices, where those devices don't have the graphic processing units to do this, the GPUs, or may have limited battery life. So it's often a good approach to just offload this to nearby server. Okay, so that's one approach. And even if you have good processors, you might still want to do this for other devices, IoT devices, AR headsets, and so on. Okay? And the reason this is now called mobile edge computing is these types of applications are becoming even more popular with 5G and so on, because you can get good bandwidth to cellular networks. So even cellular companies are beginning to put edge servers near cell towers. Okay? So you essentially ask for some service, your phone connects to a cell tower, okay, there is already compute and storage nearby, so you can deliver applications from near cell towers or somewhere nearby. Okay? So, and all of that is now being used for all kinds of other applications, autonomous vehicles and industrial automation. They all might need local compute. If you're self-driving cars, you can't take all of the compute and put it in the car. You might need compute nearby to do other kinds of computation for you, not the driving part, but all kinds of other processing has to be done, so you can know what are road conditions, is there any problem on the road, are there weather issues. All of this kind of services can be provided at low latency because the car is driving, so you may need to provide it very quickly so that the users have drivers. In this case, it's a program that's driving the car, but that the driver of the car, which is the software, gets up-to-date information. Okay? So all of these new use cases have increased the need to deploy a lot more edge computing today. Okay? And with deep learning, this has essentially become extremely popular. So now you do something called edge AI. Edge AI essentially says, I train my model in the cloud. I spend a lot of compute resources, train that model, but then I deploy it at the edge, okay, for inference. The training is done in the back end. The inference is being done very close to users. So you have all kinds of new applications. You might have home security cameras that are continuously recording, and they actually go and monitor all the faces in the video, whether it's a strange object, whether it's a car. All of that object recognition is done in real time on all kinds of videos. Okay? You don't really want to send lots and lots of videos all the way to the cloud to the processing, wastes a lot of bandwidth. If you can do that processing near to where the data is being produced, okay, it reduces the latency, but it also saves network resources. Okay? So a lot more of this is happening at the edge. Okay? A lot more of these voice assistants that you see are going to start using edge services, because you just speak to something and it's going to talk back to you and tell you something. The faster the latency, the lower the latency, the better you feel. Doing this on the edge might make sense. So in this case, you might have to deploy speech recognition models and other kinds of models at the edge. Okay? So this whole field of edge computing, because of the rise of deep learning models and so on, has become even more popular, and edge AI has become a good use case for this. Okay? So you can do low latency offload, as I said, and already I said you can use this as an extension to the cloud. Okay? Lots of services I already mentioned. You can essentially get local regions in addition to global regions, get instances there. There are all kinds of these regions popping up. There's one in New York, one in Boston, all edge services. And they also provide IoT data processing. All your sensors that you're deploying everywhere, they just send data to your local edge, gets processed there. Okay? Perhaps also subjected to inference and so on. Okay? So this is where this field is today. It's actually a fairly recent development. So the research on edge computing is still very much in its infancy. Many conferences in this field for people who are doing research to publish new research and so on. So you will see all kinds of new papers appearing on this even today. Okay? So I'm going to stop there, and then we'll continue next time.